Chapter 23, Computational Chemistry, Section 23.3, the Hartree-Fock method and the basis sets. The essence of the Hartree-Fock method is to break a many-electron Schrodinger equation into many one-electron Schrodinger equations. In the one-electron equations, the electron-electron repulsion operators are replaced by the mean field one-electron operator. One difficulty in the Hartree-Fock calculations is that one must make an initial guess of those one-electron wave functions, one for each electron, to start with. Another difficulty resides in solving these one-electron Schrodinger equations. To resolve these issues, it is common to parameterize some Gaussian functions and then use the linear combinations of these pre-parameterized Gaussian functions to describe the waves of the electrons in the atoms and in the molecules. The set of such pre-parameterized Gaussian functions is called the basis set. The Hartree-Fock method is then simplified to the optimization of the coefficients of these Gaussian functions and the coefficients in front of the linear combinations of those Gaussian functions. For example, in the Hartree-Fock energy calculation of the H3 plus molecule, the wave function of the hydrogen y-s orbital can be expressed as a combination of three Gaussian functions. So over here we have 1, 2, 3 Gaussian functions, and this is called STO3G basis set. STO stands for Slater type orbital. 3G stands for 3 Gaussian. So you can see there are 3 coefficients in front of the Gaussian functions, and also you can see those exponential parameters. All those numbers are predetermined before the calculation is conducted. In the STO3G basis set for the hydrogen atom, the wave function of the y-s orbital of each hydrogen is expressed as a combination of 3 Gaussian functions. So you can see e to the power of -3 r squared, e to the power of -0.6 r squared, e to the power of -0.17 r squared. So these 3 Gaussian functions have different distributions. Over here we have -3.4, therefore this Gaussian function is very tight with a narrow distribution. And here this Gaussian function has a wider distribution. And then we put some coefficients in front of those Gaussian functions and pre-optimize those coefficients as well. Now let's look at the shape of the combination of these 3 Gaussian functions. It looks like this. It's still a bell shape, but it looks awfully similar to e to the power of -r, the exact wave function in the hydrogen atom. Let's compare these 2 shapes. We have the linear combination of 3 Gaussian functions here as the blue curve, and the red curve is e to the power of -r, which is the exact wave function in the hydrogen atom. In the STO3G basis set, the wave function of the y-s electron of the hydrogen atom is expressed as a linear combination of 3 Gaussian functions, denoted by 3G. The exact expression is e to the power of -r. So why do we need to use those Gaussian functions, not directly the exponential functions, to describe the electron waves? Well, the main reason is this. When we calculate the electron-electron repulsion using a computer, it's awfully faster to use Gaussian functions instead of exponential functions. When more Gaussian functions are used, the accuracy is further improved. So right now we're comparing this original STO e to the power of -r, the red curve, so it's somewhere here, with STO1G. This is just one Gaussian function, thus 1G, STO3G, this is STO3G, still look like a bell shape. And then STO5G. So STO5G, it's very difficult to see STO5G because STO5G almost matches with the original e to the power of negative r exactly. What if we use more Gaussian functions? Well, again, we'll get better and better accuracy using more and more Gaussian functions to match with the exact exponential solution. But the downside is we will have to use more computational resource to conduct such a calculation. How do we determine the molecular orbital coefficients when we calculate the energy of a molecule? Well, in this H3 plus molecule, we use as example here. There are 3 MOs because we start with 3 AOs, 1 AO from each hydrogen. And the 3 MOs are denoted by psi of MO1, psi of MO2, and psi of MO3. They're all linear combinations of the 1s atomic orbitals of the 3 hydrogen atoms. The essence of the Hartree-Fock calculation is to optimize the molecular orbital coefficients. So those C's, C1J, C2J, C3J. So in this equation, J is from 1 to 3 because we have 3 1s atomic orbitals centered on these 3 hydrogen atoms. Therefore, we have C11, C12, C13 in this equation. We have C21, C22, C23 in this equation. C31, C32, C33 in the third equation. So really, in the end, we actually use linear algebra to solve these equations to optimize those molecular orbital coefficients, the values of those C's. C sub ij is the molecular orbital coefficient in the J's equation, and this I is in front of in the ith equation, and this J is the label for the 1s orbital here. The total wave function of the 2 electrons in the H3 plus molecule may be expressed as a 2 by 2 determinant. So since we have 2 electrons, we need to make sure this wave function is anti-symmetric upon the exchange of the 2 electrons. Therefore, we use a determinant here. Assuming psi 1 and psi 2 are both normalized, we need to have this 1 over square root of 2 factorial here because a 2 by 2 determinant contains 2 factorial terms. So this is just to normalize the total wave function. And then we expand this determinants. We get psi 1 of 1 times psi 2 of 2 minus psi 1 of 2 times psi 2 of 1. So psi 1 is going to be the first MO with alpha spin. And psi 2 is going to be also the first MO with beta spin. This is a typo over here. It should be psi of 2. Again, psi of MO1 is the lowest energy MO. All 3 1s atomic orbitals are in phase. And then we can compute the child energy of psi 1, 2. And we can minimize this psi 1, 2, which is going to give us these MO coefficients. The larger the basis set we use in the Hartree-Fock calculation, the more flexible and accurate the wave functions can be. The 631G basis set is one of the larger basis sets, STO3G. So over here, 3G means 3 Gaussian functions, and 6-31G, what does that mean? Well, 6 denotes a linear combination of 6 Gaussian functions used to describe every core electron. 3-1 denotes a linear combination of 2 linear combinations of 3 and 1 Gaussian functions for each valence electron. They are separated by this hyphen here. So core electrons hyphen valence electrons. So look at here, it's a linear combination of 2 linear combinations. So this 3 means a linear combination of 3 Gaussian functions, and this 1 means a linear combination of only 1 Gaussian function. And then we have a linear combination of these 2 linear combinations. And we have a coefficient for each of these 2 linear combinations that can be optimized in the calculation. Again, G stands for Gaussian, and this hyphen separates the core electrons from the valence electrons. For the hydrogen atom, we do not have any core electrons, so it's going to be just 3, 1 for the valence electron in the hydrogen atom. Alright, over here you see a linear combination of 3 Gaussian functions. Over here you see just 1 Gaussian function here. The values of A and B are optimized in the Hartree-Fock calculation, including the predetermined parameters in the function. We have this. Again, A and B will be optimized in the actual Hartree-Fock calculation, but all other parameters, such as the coefficients in front of the Gaussian functions, those d's, and also the exponential parameters, those zetas, they are predetermined. So for example, we have a linear combination of 3 Gaussian functions here, 0.3 times e to the power negative 18 r squared, a very narrow distribution here, and then e to the power negative 3 r squared, a wider distribution, negative 0.6 r squared, even narrower, and over here a really narrow Gaussian distribution here. So compared with the STO3G basis function, which contains only 3 Gaussian functions, the 631G basis function is more flexible and can be used to describe the wave of the electrons more accurately. Well, not only we have more Gaussian functions, but also remember this: the values of A and B can be optimized in the calculation, while in this STO3G all parameters are predetermined. So when you have more flexibility, you always can describe the electron waves more accurately. Again, the larger the basis set is used in the Hartree-Fock calculation, then the more flexible and accurate the wave functions of the electrons can be achieved. And also, if you have more parameters to be optimized in the calculation, and then we have more flexibility and more accurate. In the 6-31G basis set for the lithium atom, we have both core electrons and valence electrons. They are treated differently. For the 1s core electrons, we use a linear combination of 6 Gaussian functions. The 6 coefficients are predetermined. Over here, the 6 coefficients are here. And zeta, we have 6 different zeta values. They are here. And you can see this one is 642. So it's 0.6 times 10 to the power 3, so it's really 642. So if you have a function that is e to the power of negative 642 r squared, this function is extremely narrow. And over here we have a wider distribution. All right. So we use the linear combination of the 6 Gaussian functions with this coefficients and corresponding exponential parameters to describe the core electron in lithium. Again, when you have a zeta of 642, this is very tight. But if you have a zeta of 0.6, it's pretty loose. We're just using a combination of tighter Gaussian functions and looser Gaussian functions to describe, the electron wave more accurately. Again, the larger the basis set is used in the Hartree-Fock calculation, the more flexible and more accurate we can achieve. In the 6-31G basis set for the lithium atom, again, the core electrons and the valence electrons are treated differently. We use a linear combination of 6 Gaussian functions for the core electrons. Now for the valence electrons, we use 31G. That means a linear combination of 3 Gaussian functions and also a linear combination of 1 Gaussian function here. And overall, it's a linear combination of 2 different linear combinations, all right? Because the values of A and B will be optimized in the Hartree-Fock calculations. This is the 2s atomic orbital. We know there should be a spherical nodal surface So we need to include this as a part of the wave function r minus a. A is just the radius of the spherical nodal surface. This can also be pre-optimized. This can also be computed. Now let's look at 2px, 2py, 2pz orbitals. Each of them has a planar nodal surface, so that's why you can see we're going to have this psi of 2px over x, 2py over y, 2pz over z as a linear combination of two linear combinations. The first linear combination, we have three Gaussian functions. The second one, we have only one Gaussian function. And then we have those coefficients and exponential parameters. Alright, so the zeta values are here for this combination, and the zeta value from this zeta prime is this. What about the coefficients in front of the Gaussian functions? For the 2s orbital, we use these three coefficients. For the 2p orbitals, we use these three coefficients. Alright, for this, the first linear combination of three Gaussian functions. For the second linear combination of only one Gaussian function, we use this coefficient for the s orbital, this coefficient for the p orbital. So these two actually are the same. It's just this is just one, this is just one. We can use a larger basis set to describe the electron wave even more accurately. For example, 6-311G. Well, in this case, we'll just use three linear combinations for each valence electron. The first linear combination contains three Gaussian functions. The second one, only one Gaussian, and then another Gaussian. So this is how we make it more flexible. And then we can look up those coefficients. We can look up those zeta values from the database. The value of A, B, and C should be optimized in the actual Hartree-Fock calculations. This 6-311 plus GD basis set is even larger than this one. So this plus means we're going to employ very, very loose diffuse functions for non-hydrogen atoms. Alright, they're called diffuse functions. They have a really wide distribution in space. Diffuse functions are often used for anions or molecules with loosely bound electrons. And D means we're going to use D-type polarization functions on second row atoms like carbon, nitrogen, oxygen. The inclusion of those polarization functions allow for more flexibility. For example, if we have like some bonding orbitals, we know the bonding orbitals are supposed to be linear combination of atomic orbitals, but there's some distortion to those atomic orbitals. For example, when a pi bond is formed between two 2p orbitals centered on two carbon atoms, these 2p orbitals are slightly distorted in the direction of the molecular axis to have a better overlap. Now this distortion can be better described with the addition of D-type functions. So they look like D orbitals in the basis set. So this 3-311 plus GD basis set is sometimes also written as 6-311 plus G star. It's just by convention. This star means just D polarization functions on 9 hydrogen atoms. So I mentioned that if you have plus, that means diffuse functions on non-hydrogen atoms, for loosely bound electrons. And I mentioned this D is the D-type polarization functions on non-hydrogen atoms to better describe the distortion of the atomic orbitals when they form bonds. But what about hydrogen atoms? Well, we can use an even larger basis set. This is 6-311 plus plus GDP. So now we see three pluses. That means not only we have diffuse functions on non-hydrogen atoms, but also we have diffuse functions on hydrogen atoms. Alright, diffuse functions have really wide distribution. They're used to describe loosely bound electrons. For example, if you have anions, if you have excited states in which electrons are loosely bound, and then we need to use diffuse functions. Now here, D and P over here, that means D-type functions for non-hydrogen elements like carbon, nitrogen, oxygen, fluorine. And then P-type functions for hydrogen. We know in a hydrogen atom, supposedly this electron should be in the 1s orbital, but by adding those P-type functions, we can better describe the distortion, when this 1s orbital on hydrogen atom forms a bond. So even in a hydrogen 2 molecule, the electrons are not really like two spheres on the two hydrogen nuclei. There is some distortion that can be better described by including some p-type functions. This 6-311++ GDP base set is sometimes written as 6-311++ G star star. 2 stars means D-type polarization functions on like non-hydrogen atoms, and the second star means p-type functions on hydrogen. We can even add more polarization functions. So we just changed this dp to 3d and 2p. So we have 3 sets of d-type functions on carbon, oxygen, nitrogen, and 2 sets of p functions on hydrogen atoms. Again, when we have a larger number of Gaussian functions, we can describe the electron wave more realistically, more accurately, or get better trial wave function and lower trial energy. The more flexible the trial wave function is, the lower the trial energy we can achieve, and the lower the trial energy, the closer it is to the exact energy in the Hartree-Fock calculation. In general, using larger basis sets often results in more accurate calculation, but it does require more computing resources. So we have to balance the accuracy and efficiency. There are numerous types of basis sets that vary on the number of Gaussian functions, the coefficients, the exponential parameters. And they also vary in the number of polarization functions, diffuse functions, and their parameters. So how many basis sets are there? I think there are at least several hundred different kind of basis sets. And you can find the most commonly used basis sets in this website. You can just Google basis set exchange and you can find this website.